So, hello everybody, and welcome to our interview with Quentin Ochem, a business development lead at AdaCore. Prior to our digital event, ScaleUp's OSS.5 Europe, the digital event on functional, operational, and system safety of autonomous driving, we caught up with Quentin to discuss some challenges of this industry. Hi, Quentin, welcome. Would you like to briefly introduce yourself? Like, how long are you at AdaCore and what are your main tasks?
Sure. So my name is Quentin Ochem. I joined the company quite a few years ago, actually in 2005, straight after university. I've stayed with AdaCore ever since. I started as a software engineer and I slowly moved to more business responsibilities. So right now, I am responsible for the product management of our core product, the GNAT Pro ADA tool suite. But I'm also responsible of business development, and in particular, how to bring our solutions, which have had a long track record in domains such as aerospace and defense, to new domains, and in particular, how they would fit the current challenges of automotive.
Okay, thank you. So then, without further ado, let's start with the first question, which is, so the solution, your solution at ScaleUp OSS.5 Europe is announced under the title Engineering Self-Verified Software. What is the most important message to the participants and your potential clients in this context?
So maybe I can start back from the common wisdom with regards to development and verification, where in a lot of places you hear that you need to have those activity independent, right? You need to have the developer, which is different from the verification engineer. The issue is that if you implement that, what tends to happen is that people doing software development don't care too much about the way their software is going to be verified. And as a result, people that are starting the verification may have a hard time checking certain aspects, certain requirements on the software. What we've seen from the field is that that independence is actually harmful if you completely separate those two things. It's better. Yes, you need somebody to be here to verify what you're doing, and you need that person to be somewhat independent, but you also need yourself to, as a developer, right, to worry about whether or not the software that you're doing is doing what is expected to be doing. So you need to have consideration for specification to start with, how they are being defined, what they mean, how they're being encoded in the whole system. And then you need to worry about how are you going to architect the application so that verification is possible. And there are ways to go actually further than that and provide means to allow development engineer to embed in the software itself both the actual code and aspects of its verification. And we think that this is something very important to do. This is something that is streamlining the process, and ultimately will have two important outcomes. First, it will reduce the overall risk of introducing mistakes because you're worrying about verification and checking things as a developer. And second, perhaps even more importantly, it will reduce the costs of the entire development process because you are sort of frontlining some of this consideration, whereas in some other development processes, they would happen very late, and then the later you find a problem, the more expensive it's going to be for the whole company to fix.
Yeah, absolutely. Okay, thank you. And so what do you consider to be the unique selling point of your solution, of your approach at AdaCore?
Okay, so once we've said what we said before, right, you want developer to worry about verification. The next step is that you need to give them a platform for being able to do at the same time development, verification, and if possible, also formalize the requirements that are being verified. And this is really what we are providing here. It turns out, in terms of unique selling point, right? It turns out that integrating everything on a software environment that is based on something like the C programming language, for example, is very difficult, because the language is not meant to be used in this way. So you end up needing a lot of extra tools and formalism to put all the pieces together. You're going to need to have the C language, you're going to need to have some extra language, maybe in the form of specific formatted comments to express requirement, intention, constraints. You're going to need tools that are able to understand these comments, make the link with the code, perhaps generate tests or feed into static analysis later on, so on and so forth. It's a very difficult environment to set up, and because it's all pieces that have not been designed from the get-go to work together, it can go to a certain level, but you will encounter limitations fairly quickly. That's what we've seen, at least on the solutions that have been experimented in the industry. What we offer is something different. We are going to start from a different programming language, which is called Ada, or Ada Spark. That's not to say that you cannot work in a C environment. As a matter of fact, all of our customers have a lot of legacy C. But for the new modules or new capabilities being developed, they would not use C, they would use the Ada language. And the value of the Ada language is that in the programming language itself, with the same formalism that you would use to develop your actual functional and operational code, you're going to be able to describe constraints on the code, something like that type has a range of value that is only this. This thing is actually not a pointer, it's an array, and so on and so forth. And you're going to also provide the means to automatically verify those constraints that you're describing in the code. So all of a sudden, as a software engineer, with the very formalism I'm using to write code, I can also write or transcribe specification and constraint. And those two things between tightly coupled, tightly consistent, I can also enable all the kind of verification that I will need to do at that level, all at the time where I'm developing software. I don't need to wait weeks or months for somebody to come to verify it. And that sort of allows to achieve the kind of increase of safety and cost cuts that I was describing in the previous question.
Okay, thank you. That sounds really great and fascinating. And well, if you think of your clients or potential clients' requirements, which problem areas in context of functional, operational, and system safety in autonomous driving do you think is especially critical?
So I'm going to take a little sideway to answer your question. I think that in terms of technology and methodology, there are options out there that people can adopt today, including ours. I think that the real difficult question to answer, at least from our customer standpoint, is manpower. If I quote one of our customers, one of our largest customer, when they adopted Ada on Spark, their comment was, we had to tackle those high integrity, high safety, security needs today that were not here 5 years or 10 years ago. And we realized that we can't hire our way out of this problem. There are not enough skilled resources out there. Of course, if you have one very talented developer, you're going to be able to give him anything. He's going to be able to do very fine software that's going to be highly reliable. The issue is that how do you move from there to a situation where you have a team of 50, 500, maybe even more developers? You're not going to be able to have the same high level of quality of skill sets consistently, and even further down the line in time, you're not going to be able to maintain that through the 5-10 years that the project might need to be at least maintained. So I think that's the issue. And once you said that, you sort of start to think differently on the way you tackle this problem. Okay, let's accept the fact that we're not going to find manpower that is at the necessary skill level to tackle our problem. So maybe we need to go one step back and acknowledge the fact that whomever we find, we're going to have to train. We're going to have to ask them to do something maybe a bit different. And then what can we change at the technology level to sort of lower the level of demands that we have on these people that we're hiring, right? What can we do to make that easier for an average software developer like myself to get integrated into this environment that has this level of demands? And that's where the technology that we're providing provides an in, because there's the fact that you include verification at the developer desks also means that there are a lot of things that you can automate. And the more you automate, the less you have to rely on the fact that you have super skilled developer, and perhaps also the less you have to spend your super skilled developer time onto mundane issue. You can get them to concentrate on the very hard issue. And I think that is something that we help the industry at large with.
Okay, yeah, thank you. And so what do you think are the best approaches or technologies to meet these challenges?
Okay, so let's talk a little bit about what we mean by verification, right? Traditionally, verification is testing and perhaps a bit of static analysis. So what is that? Testing is to say, I'm going to have actually a relatively small sample on the possible input to my application. And I'm going to hope that the way I craft this sample is representative enough so that it caters for all the possible situations that the software might face in real life. But I don't know if that's the case or not. So I have techniques such as structural code coverage or equivalence classes and so on and so forth to sort of gain confidence on the fact that I've tested enough. But truth being told, I don't know if I tested enough. That is usually complemented by something called static analysis, where instead of dynamically at runtime testing the software, I'm going to have a tool that is going to look at known error patterns on my code. And from those patterns, it will be able to detect some potential problems. But that's not foolproof either, right? I have patterns, so I can tell you as a static analyzer, you got this and this problem, but I cannot tell you, you don't have any of that specific problem, or you cannot demonstrate that specific property that you're trying to demonstrate. These techniques allow to reduce the odds of mistake. The issue is that in modern world, in particular, if you're looking at something like autonomous cars, you're going to have systems that not only need to be safe, that is to say they have low odds of failure, but they also need to be secure. That is to say they resist to malignant attacks, from hackers and so on and so forth. When you start to enter the realm of security, you don't want to have low odds of having errors. You want to have none. Like if I take something as a buffer overflow, which is probably the most common source of an attack backdoor, you don't really care if you have 1,000, 10, or even one potential buffer overflow. If you have one, you can be sure that an attacker will be here and will be able to find that very one, even if in normal operation, it would be extremely unlikely to be triggered. So testing, static analysis is great to reduce the odds of having those problems. But to go to the place where you have enough confidence that something like that does not happen, to get to a place where you have a guarantee that does not happen, you need to use something different. So what our technology provides, and yes, it provides ways to test and way to do static analysis, because that needs to be part of your processes regardless. But because we have all this information in the code that was described before, and because the language itself has been crafted to allow to go to the next level, you can deploy something, you can deploy a verification methodology called formal proof. It's a bit like static analysis in the way, except that instead of trying to apply code patterns on your code, you're going to create a mathematical model and demonstrate that this mathematical model of your code is correct. And thanks to the fact that, again, I have the one language, the one formalism to describe everything, it is surprisingly easy for an average developer like myself to achieve something such as guarantee of absence of buffer overflow, like with a little bit more effort than I would put, than I would normally put to develop my code. I can get sort of a stamp by the tool. Yes, you don't have buffer overflow, and that's kind of the ground level, if you will. That's something that pretty much anybody with an engineering degree can reach. But then once you get there, you can start to look at some more complex properties that you might want to describe on your code, and also describe this property formally and verify them formally. So part of the actual requirement of your application that used to only be able to partially verify through, for example, testing, now you are able to fully verify with formal methods. And that is very important, because not only do you ensure that you cannot have flaws on those very specific properties, so that's, again, an increase in terms of the safety and the security of your application. But once you have the proof that this is correct, you know that that's not going to sort of blow in your face, if you allow me that saying, at the end of the process, where things can be very expensive. So again, that's also a mean to reduce the cost. What that does require, though, is to acknowledge the fact that there is potential value in trying to develop software differently, which is typically the place where you need to spend more time, have more discussion, and perhaps start to do a little proof of concept or something to convince yourself that, yes, this is the kind of methodology that can be adopted wherever that is that I'm working.
Okay, great, thank you. And how do you yourself assess the developments on the market for solutions for vehicle automation for the next, let's say, 1-2 years?
So I think there's an issue that needs to be solved and is not quite solved yet. I don't know if it's 1 to 2 years or if that's going to take more time. But if you look at something particular like autonomous vehicles, you have this. I'm sorry about that. You have this seemingly contradictory ask. On one hand, you want very capable cars. You want the car to drive by itself, to be able to drive in various contexts, various weather conditions, various road conditions, and so on and so forth. So that's a lot of capabilities. But at the same time, you want your car to be safe. You want him to do no harm to yourself or to your surrounding. And if it can also avoid doing harm to itself, that's yet another additional benefit. The issue is that those two requirements, those two demands, are fundamentally contradictory. If you look at the kind of technology that you need to get the car more capable, you're going to look at something like machine learning. There is very little way to ensure the safety on those systems. We barely understand them. And we know that we can only describe them in terms of probabilistic. You know, we know that they are working in 99.99% of the time because that's what we observed. But we have no way to say, yes, I'm sure that this is not going to be, that those situations that I'm afraid of are never going to arise. So how do you bring those two work together? And I think that's, again, a place where, at least in the next 1 to 2 years, and perhaps even beyond, there's going to be a lot of effort being spent. Of course, the way to do that is to actually develop two systems, right? You have the system that implements the capabilities, and this one you don't trust. I mean, you trust as much as you can, but you don't trust from a safety standpoint. And then you have another system around it, which is going to be the safety harness, maybe. And that system, which is going to be much less capable, is not going to be able to drive your car, but it's going to be able to tell, okay, well, here you're outside of normal operation, you are reaching a danger zone, I'm going to do whatever I can to, I don't know, park your car or put it in a safe place, put it in degraded mode and what have you. And I think that this is really where the mixing and matching those two sides of autonomous vehicle work is going to be very interesting in the next few years. Here at AdaCore, with our technology and our solutions, where we shine, where we can provide value is definitely on that second edge. Like, how do we help you to gain as much trust as you can into the safety harness that is surrounding the core of your system?
Okay. Yeah. Thank you. Thank you, Quentin, so much for your time. Thank you for this great interview. Also, everybody who will be watching this interview later, please feel free to register for AdaCore session. This digital event, ScaleUp OSS.5 Europe, is on 16th and 17th of June online. So please sign up and join us right from your desk. Thank you again, Quentin. This was really great.
Thank you.
And yeah, have a good time. Have a good day. Bye-bye.
Bye.